Let's take a look at some Lewis dot structures for some simple compounds. Now, before you dive in to these examples, I hope you have read your class notes and your textbook regarding how to determine the number of valence electrons and how to write Lewis dot structures for simple elements. Okay, so let's dive into this. First, we have a compound H2S. Okay, when drawing Lewis dot structures, one of the most important things is to first determine the total number of valence electrons. Okay, so for hydrogen, they have one valence electron each. Now remember, how we determine that is we look at the main group elements, the S and P block as we call it, and we count what column they are in, what group, and that tells us the number of valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Okay, so we look at the S and the P block, and we determine those valence electrons. So hydrogen has one, sulfur is right here, that is in the 1, 2, 3, 4, 5, 6, the sixth column, so it has 6 valence electrons. Okay, so our total number of valence electrons here are 8. Okay, that's most important because that is the only electrons you can use. Okay, that's it. Those are it. So we put sulfur here in the middle as our central atom. Now I have designated who the central atom is in each one of these for you. Okay, so again, if you need to review how to determine the central atom, reference your class notes, reference your textbook. Okay, I just want to show you how to draw some real quick here. Okay, and then we connect the hydrogens by single bond. Now remember, hydrogen could never be a central atom because it can only form a duet rather than an octet. Okay, so it's always going to be one of the add-on, the bonded atoms to the central atom. Okay, so here we have connected them by single bond. Okay, and it doesn't matter if you put them on the side or on the top and bottom, because again, remember, Lewis dot structure is a two-dimensional, a flat surface drawing of a three-dimensional reality, that is, reality three-dimensional molecule here. So around the sulfur now, we've achieved a single bond here, that's 2 electrons, 3, 4, 5, 6, and then another single bond giving us 7, 8, giving us the octet achieved around the sulfur. Well, let's move to this next one here. CH2Br2. Okay, again, first thing, let's get the number of valence electrons. Around carbon, there's 4. 1, 2, 3, 4. It's in the fourth column. Hydrogen has 1 apiece again. And then the bromines. Bromines are over here in the halogen group, right below chlorines. So that's 1, 2, 3, 4, 5, 6, 7 in that 7th column. So 7 valence electrons it looks like for the bromines. So 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. Okay, so again, let's get our total number. 7, 7, 1, 1, and 4. That's 7 and 7 is 14, 15, 16, 17, 18, 19, 20. We have 20 valence electrons total. That's what we're utilizing. Okay, I've designated the carbon being the central atom, so let's put it in the middle. And let's go ahead and connect the hydrogens by single bond. Okay, so you can put them on either side or top and bottom, left, right. Okay, just connect them to the carbons there, because remember, it's three-dimensional. Okay, so there we have them. They formed their duet. They're complete. The bromine, let's connect it to the carbon by single bond. And then let's go ahead and put those remaining lone pairs of electrons on those bromine. Okay. Now let's count this up. The hydrogens have formed the duet. They're complete. The carbon, 2, 4, 6, 8, 8 electrons through these 4 bonded pairs. So it's completed an octet. Very happy. And the bromine has 2 electrons being utilized through this bonded pair, and then 2, 4, 6 in lone pairs here. So that gives it a total of 8 surrounding it, so it's achieved an octet in each location. And to prove that the 20 electrons are all we used, let's count those. 2, 4, 6, 8, 10, 12, so 12 in lone pairs, and then 14, 16, 18, and 20. There's all 20. Okay. Now let's move over here to the HCN. Okay, to the HCN. Let's first count up our valence electrons. Hydrogen has 1. Carbon again has 4. Remember, we're doing that by looking at the periodic table. Carbon's in this 4th column. And then nitrogen is right next door, so it will have 5. So remember, we want to get that count. Okay. So we have a total of 10 valence electrons. That's what we can utilize. Okay, 10 valence electrons. Okay, so, and I've shown you that the carbon goes in the central position. Okay, so there's those 4. Now let's connect the hydrogen by a single bond, because that's all it can do. That gives it its duet. It's complete. Let's take the nitrogen and attach it, okay, by a single bond. Okay, there we are. Okay, so we've got that attached. Now, let's see. Once we've got these single bonds, we need to count up to see what we've achieved. The hydrogen is complete with its duet. The nitrogen here has 1, 2, 3, 4, 5, 6. Only 6 electrons surrounding it. 4 in lone pair, and then these 2 bi-bonded. And the carbon has 2, 4 through bonds, 5, 6. So it has 6. So both these nitrogen and carbon are short. Now, that's when we can utilize double and triple bonds. Now, double and triple bonds, carbon, oxygen, and nitrogen are great at utilizing double and triple bonds. Okay, carbon, oxygen, and nitrogen. So what if we take this electron and one of these from the nitrogen and we utilize a double bond? Okay, that would then give this carbon 2, 4, 6, 6 through bonded, and a 7th sitting here alone, so it's still short. The nitrogen now would have 2, 4, 5, 6, 7. So it would have 7. So both of them would still be 1 short. So now let's utilize another electron from each, and we'll share those, and we'll form us a triple bond. And let's see what that does. That gives us hydrogen with its single bond, a triple bond between the carbon and nitrogen, and we still have, there on the nitrogen, we still have these 2 lone electrons that are bonded. And let's utilize that. Okay, let's see, 2, 4, 6, 8 around the carbon. That's a good octet. And around this nitrogen, we have 2, 4, 6, 7, 8. We have 8 electrons around it. But notice, we still have only utilized 10 total electrons. 2, 4, 6, 8, 9, 10. Okay, so that's complete. So we've got a triple bond between the carbon and nitrogens, and we've got a single bond through the hydrogen and carbon. We still have a lone pair on the nitrogen that is not bonded. Okay, now let's try this final one with SO3. Okay, now notice on this, sulfur and oxygen are both coming out of the same column. So they're going to have 6 electrons, that is valence apiece, 5 and 6. Okay, and the oxygen, we're going to have 3 of those, 2, 4, 5, and 6. So we're going to have a total of 24 valence electrons here. Okay. And I've underlined here, sulfur is going to be our central atom. Okay, so sulfur with the 6 valence electrons. Okay, let's take these oxygen and let's bring them around. Let's connect by a single bond. Okay, there's the first oxygen connected. Let's connect another oxygen. Okay, with a single bond right there. Okay, let's connect a third oxygen by a single bond. Okay, so we've got them all attached. Now let's make sure we still have all 24. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so we still have all 24. We've got them attached by single bonds. Okay. Now let's see, this sulfur looks like it's got 2, 4, 6, 7, 8, 9. Looks like it has 9 around it. And so that doesn't look well. And then oxygen here, 1, 2, 3, 4, 5, 6, 7, only has 7. So it looks like we're coming up short here. It looks like these oxygens don't have enough electrons around them, and this sulfur looks kind of like it has too many around it. Well, when this happens, when it looks like that, think of double and triple bonds. And remember that carbon, oxygen, nitrogen are rather good at forming double bonds or triple bonds. So let's try a double bond here around this sulfur. So let's just try this. Okay, let's just utilize this right here. Let's try this. Okay, so let's try this. Now remember, you can pick any of these to try the double bond between. Okay, so now what that would give us is that would give us this a double bond with here. Okay. Okay, so we have this template so far. Now remember, these electrons are being shared, so you can move them where you need to move them. Okay, I like to call them community property. And you have a total of 24 to play with. So right now we've got 2, 4, 6, 8 around this sulfur being utilized in bonds. This sulfur has an octet. It's complete. This oxygen right here has 2, 4, 6, 8 utilized around it, so it's complete. So what we need to do is we need to get all these lone pair electrons, we need to get them around these two neighboring oxygens to complete them. So let's put 6 around them. Okay, there goes that one. So it's complete. 2, 4, 6, 8. And then around this one, 2, 4, 6, 8 through the bond. Okay, now let's count up because this is a lot of drawing here now. This is what we've come up with so far. This right here I'm boxing. We've got 24 total. 2, 4, 6, 8, 10, 12, 14, 16 in lone pairs. 18, 20, 22, 24 through the bonds. Okay, so there's all 24 of them. And it looks like each one of the oxygens have a full octet, as does the sulfur. Okay, but now this particular compound has something unusual. We could move this double bond over here. We could move that double bond over there. And it would be the same identical double bond. It would be a sulfur to oxygen double bond. When this can happen, this is what we call resonance. Resonance. So in this compound, there isn't 2 single bonds and a double bond. There's actually 3 perfectly identical bonds, because any of these bonds I could have drawn as the double bond. But in reality, there isn't a single bond, double bond. There's actually 3 perfectly identical bonds. They're not single, they're not double. They're a, so to say, for lack of a better word, a hybrid of those two. It's what we call resonance, when you can move a double bond to a different, in this case, sulfur-oxygen pair, and end up with an octet. Okay, that double or triple bond can rotate, can move to a different location. Okay, those bonds end up actually being identical. They aren't a true single and a true double bond. They're 2 identical bonds. It's called resonance.